Welcome viewers to the third segment of the seventh lecture for the online series of lectures for the course of Algebraic Topology 1. We are going to begin this segment with an example. Example 5, where we have to compute the homology groups of a given simplicial complex. So suppose we have the following two-dimensional complex L whose underlying space is a square. V0, V1, V2, V3 are the vertices, and the edges are given by E1, E2, E3, and E4, and there is one more edge called E5. Okay, and two simplices both oriented counterclockwise. One is sigma 2 and the other one being sigma 1. Okay, this is figure 5, two-dimensional complex L. Okay, the underlying space mod L is a square. In this example, the general one chain C is given by C equal to sum over I Ni Ei, okay, where Ei are the elementary chains corresponding to the oriented one simplices Eis. Okay, so E1, E2, E3, E4, and E5 are the oriented one simplices, right, given in this figure 5. And in this sum, these Eis are the elementary chains corresponding to these oriented one simplices here in this complex L. Okay, so C can be written as a linear combination of elementary chains N1 E1 plus N2 E2 plus N3 E3 plus N4 E4 plus N5 E5, where Ni's are integers. This is equation number 8. So it turns out that del 1 C, which is a zero chain, right? This zero chain is given by N1, and del 1 acting on E1 gives V1 minus V0, N2 times V2 minus V1, and N3 times the boundary of E3 is V3 minus V2 plus N4 times V0 minus V3 plus N5 times V2 minus V0. Okay, so this can be manipulated to look like the following: N4 minus N1 minus N5 times V0 plus N1 minus N2 times V1 plus N2 plus N5 minus N3 times V2 plus N3 minus N4 times V3. This is our equation number 9. Okay, hence the one chain given by equation number 8, hence the one chain given by equation 8 is a one cycle that is del 1 of C is equal to 0 if its value, if the value of del 1 C, this zero chain, if its values, what are the values? N4 minus N1 minus N5, N1 minus N2, N2 plus N5 minus N3, and N3 minus N4. There are 4 values. On the vertices V0, V1, V2, and V3 respectively are all 0. And only then C will be a one cycle, we know. So this gives us the following equation. N4 is equal to N5 plus N1, N1 is equal to N2, N3 is equal to N2 plus N5, and N3 is equal to N4. Right? So this equation reduces to the following. N1 is equal to N2, N3 is equal to N4, right? And N5 is equal to N3 minus N2. This is equation number 11. So from 11 one finds that there are 2 degrees of freedom, right? N1 and N3. Or one can take them to be N2 and N3. There are 2 degrees of freedom. One can assign the values N2 and N3 arbitrarily to obtain the values of N1, N4, and N5, N1, N4, and N5 following equation 11. Okay, so expressing N1, N4, and N5 in terms of N2 and N3 in equation number 8. Let me write equation 8 again, which is the general expression of this one chain C n1 e1 plus n2 e2 plus n3 e3 plus n4 e4 plus n5 e5. Okay, so this reduces to n1 is equal to n2, right? N2 e1, and then n2 e2, n3 remains as it is, n3 e3, and n4 is n3 e4, and n5 is n3 minus n2 e5. Okay, so this gives us n2, so n2 is here, n2 is here too, n2 is here, so n2 e1 plus e2 minus e5. Okay, plus n3 is e3 plus e4 minus e5. This is our equation number 12. So what is this? So this C, the generic expression, this is the generic expression of one cycle. Okay, and which turns out to be generated. So this group Z1 of L, okay, which is the group of one cycles. This is free abelian of rank 2 generated by these two two sets, Z1, two sets of elementary one chains. Z1 of L is free abelian of rank 2. A basis consists of the one chain E1 plus E2 minus E5 and E3 plus E4 plus E5. I'm sorry, I think they are not elementary chains. So we have a basis which consists of two one chains, which are each of them of which is a linear combination of the elementary chains. Okay, E1, E2, and E5 are elementary chains. Okay, so it's a one chain whose value on E1 is 1, whose value on E2 is 1, and whose value on E5 is minus 1. Okay, similarly, if this guy, this is a chain whose value on E3 is 1, whose value on E4 is 1, and whose value on E5 is 1. Okay, So Z1 of L is 3 abelian of rank 2, and the generator consists, the set which generates Z1 of L consists of these two one chains, each of which is a linear combination of elementary chains. Okay. On the other hand, if I take this sigma 2, the 2 simplex sigma 2, and let it be acted upon by the boundary operator del 2, then one immediately gets E3 plus E4 plus E5, right? E3 plus E4 plus E5, which is equation number 13. And if one acts the boundary operator on this simplex, on this, sorry, so this is not a 2 simplex, so you should call it a 2 chain. Okay, the 2 chain, we take the boundary of this 2 chain, which is a one chain. The one chain is given by this expression 13. The one chain acting on the edge. So the value of this one chain on the edge E3 is 1. The value of this one chain on the edge E4 is 1 also. And the value of this one chain on the edge E5 is 1. The value of this one chain on the other edges vanish. Okay. Similarly, one can compute del 2 sigma 1. Sigma 1 is another 2 chain. So that del 2 sigma 1 is a 1 chain. Del 2 sigma 1 is given by, look at this, is given by E1 plus E2 minus E5, right? This is equation number 14. Equation number 14 tells us that sigma 1 is a 2 chain, and when you act the boundary operator on this 2 chain, you get a 1 chain, and del 2 sigma 1, which is a 1 chain, is given by the expression 14. It means that this 1 chain, the value of this 1 chain on the edge E1 is 1. The value of this 1 chain on the edge E2 is also 1. The value of this 1 chain on the edge E5 is minus 1. And the value of this 1 chain on the other edges vanish. So from 13 and 14, one finds that a generic one boundary so the image of this boundary operator del 2, right? Del 2 is a map from C2 of L to C1 of L. Okay, the image of this boundary operator is a subgroup of C1 of L, right? Which is called a one boundary, or the group of one boundary. Okay. So, from 13 and from 14, one finds that a generic one boundary can be written as Z linear combination of E3 plus E4 plus E5 and E1 plus E2 minus E5, right? Hence, one immediately sees that B1 of L, which is the image of this boundary operator here in C1 of L, is isomorphic to Z squared. Okay, so the group of one boundaries is isomorphic to Z squared. Now, what was equation number 12? So equation number 12 was the generic expression of a one cycle, right? It was C is equal to N2 E1 plus E2 minus E5 plus N3 times E3 plus E4 plus E5. This was equation number 12. Okay, the generic expression of a one cycle. Right? So from this expression, one sees that the group of one cycles on the complex L is also isomorphic to Z square. Okay, one can choose integral values of N2 and N3 to satisfy 12. Hence, this group is isomorphic to Z square. Two copies of Z. Okay. Therefore, the first homology group of this simplicial complex L, which is by definition Z1 of L quotiented out by B1 of L, is nothing but 0. It's trivial, consisting of the identity element only. Okay. So now, since there are no three simplices in L, so we see that the dimension of this simplicial complex is 2. So there are no three simplices in L. Therefore, C3 of L, the group of three chains on this complex L, is equal to 0 by definition. And hence, using previous arguments, using the argument that we used in the previous example, the group of two boundaries on L is also trivial. Okay, now I need room, so let me erase things here. The generic expression for a two chain here is C2 is equal to M1 sigma 1 plus M2 sigma 2, right? This is equation number 15. So this is the generic expression of a two-chain, right? The two-chain C2 in 15 is a two-cycle if del 2 of C2, which is M1 del 2 of sigma 1 plus M2 del 2 of sigma 2 is equal to 0. That is, so we take the boundary of sigma 1, which is E1 plus E2 minus E5, right? And then you take M2 times the boundary of sigma 2, right? Sigma 1 is a two-chain, and so is sigma 2, and the boundary operator acting on those two chains will be giving us one chains. So M2 times E5 plus E3 plus E4, and this is equal to 0. And it means that so the only way this expression, whole expression, can be 0 is that M1 is equal to 0 and M2 is equal to 0. Hence we see that the group of two cycles on the complex L is trivial, right? So what does it mean? It means that therefore the second homology group of this complex, of this simplicial complex L, is also trivial. Okay. Good. So at this stage we need some terminologies. So let me erase everything. At this stage we need a few terminologies. We shall say that a chain C is carried by a subcomplex L, complex L of a simplicial complex K if C has value 0 on every simplex that is not in L. Okay, so K is a simplicial complex, and L is a subcomplex of this simplicial complex K, and we'll say that the chain C is carried by this subcomplex L if C has the value 0 on every simplex which is in K but not in L. Okay, and also we say that two P chains C and C prime are homologous if C minus C prime is the boundary of some P plus 1 chain D for some P plus 1 chain D. Okay, in particular, if C is equal to the boundary of some P plus 1 chain D, we say that C is homologous to 0, or simply that C bounds. Okay. So these notions are important for what we will be doing next. Okay. So we'll be doing one final example for this lecture. So I need to take a break. I'll be back with this final example of this 7th lecture. Thank you for attending this short segment.